Okay, we'll take two sessions, 30 minutes, 30 minutes. Okay. At 12 o'clock, I'll give you one more link. Let's see how long we can continue with the first link. Okay. In Bernoulli's equation, there are several corrections. Number one correction, he don't think fluid is a have viscosity. We ignore it. So we fix it by adding frictional head loss, right? There is a other minor correction that we assume that velocity of the fluid element, we took the average velocity q equal to v by a by q by a, v equal to, right? That means we think that q equal to a star v. From here, we figure out v equal to q by a. This is our basic equation. But this equation give you the average velocity of fluid. As also I will explain it later previously, that if you look to the velocity profile in the fluid element, we are taking only one velocity, average velocity. That means if I make a line over here, we are thinking all the fluid elements have the same velocity. So just we using like half m v square by 2g. But in reality, you see this fluid element, it don't have any kinetic energy. V is 0. Then this element V is remain very high. So if we take the average, that will be, we are sacrificing the little bit accuracy. Okay. For that reason, we use a correction factor that is called alpha, is known as kinetic energy correction factor. And it is the ratio of actual kinetic energy divided by the kinetic energy figured out by average velocity. So just remember, we need to add a correction factor with the Bernoulli's equation, and that factor is alpha. What is alpha? Actual or real kinetic energy divided by the average kinetic energy of the fluid. Now, how we can implement that correction factor with the Bernoulli's equation? So, you see, we P by right over here, V1 square by 2G, we apply the, 1 second, some people are waiting. We apply alpha 1. Similarly, at 0.2, alpha 2. Now, you need to figure out the value of alpha. If flow is laminar, then value of alpha will be 14 people waiting, it's saying. Okay. Alpha equal to 2 if flow is laminar. So you see there is a significant difference if you ignore this alpha 1 and alpha 2 laminar flow. But if his flow is turbulent, then we can use alpha equal to 1.01. Now, most of cases we have the turbulent flow. That's why we can ignore, or we can think alpha equal to 1. Because 1 and 1.05, it don't make that much difference. Then why are learning this one? But if you work in a very sophisticated program or project, say you are working for NASA, sending a satellite in the moon or Mars, and you have to derive some hydraulic equation to design something. In those cases, your accuracy is more important then you have to use this formula. Or you are designing some medical equipment, biomedical equipment. In that case, say you supplying some chemical to the human body. In that
স্যার
case, yes.
এক দুইজন মনে হয়
স্যার
ওয়েটিং
অনেকে
রুমে
ঢুকতে
আছে,
পারতেছে না,
অনেকে
ওয়েটিং
ঢুকতে
রুমে
পারছে
বসে
না।
আছে।
I admit all of them, but I think there might be network problem or okay. But we have 5 more minutes, then I have to start the next session. I see over here, but all of them join, but I don't see admit all of them. Okay. So that is the reason that you have sometime you have to work with extreme accuracy. Okay. Now, say you are rising water from your ground floor of your home to the 6th floor or rooftop. So what do you need? You have right. This is your house, and you have a water tank at the ground, and you have pump over here, right? And with this pump, you are rising water to the rooftop. So what kind of equipment you need? Only 5, right? Right now we think only 5. Is it right that we need only 5, or we need something else? Someone talking, please keep your mic unmute. Okay. You see, if you have only 5, then what will happen? You can figure out the head loss by using Darcy-Weisbach equation, FL V square divided by 2GD, right? But sometime you need to use elbow, say right over here, changing direction. And you cannot use 80 feet or 90 feet pipe. Sometimes you need to connect all the pipe together, right? That means you need to use some pipe fittings in the system. For example, if you don't have any pipe fittings, only single pipe, head loss will be less. And you can easily calculate by this equation. But if there is some other equipment, valve, elbow, union, T-joint, in that case, your head loss will be more. So how we can figure out that head loss? So there is a 2 type of head loss. Number 1 is major loss that we already figure out by Darcy-Weisbach's equation. Major head loss, that means head loss by friction. Other one is minor losses. Now, why the minor loss? Due to the fittings and change in direction. Okay. So how we'll figure out the minor loss? This is our equation to figure out the major loss. Major loss means related to the friction. But if you have the valve, bend, elbow, tees, then inlet, exit, enlargement, suddenly your pipe diameter increase or suddenly decrease. That means enlargement or contraction. So in those cases, you have to use one more equation, but you don't have to worry that much. This is our equation for major head loss, right? So you see, FL by D is a constant. Friction factor is constant. L by D is constant. So this one is the only variable right over here. So minor head loss we can figure out by using the same equation. That means this one. This constant, we think this is KL. That means minor loss due to the fittings, and B square by 2G. Now, how we will get the value of KL? There is some chart. From those chart, you can figure out the value of KL. That one mainly determined by some experiment. Okay. So how many loss we have in the pipe system? Two loss. So you just need to consider both two. Major loss in the friction. Right over here, summation. Why is the summation? You might have the same pipeline. You might have some portion plastic pipe, some portion little bit bigger diameter with stainless steel, or might have cast iron pipe. So different section has different diameter, different coefficient of friction, right? That means Darcy-Weisbach friction. So over here flow might be laminar, over here might be turbulent, over here might be again laminar. So that's why over here you give HLF1, HLF2, HLF3. So that's why we use the HL measure and summation. Similarly, you might have multiple fittings around the pipe. So you need to make summation of head loss due to the all the pipe fittings. So head loss, total head loss equal to head loss due to the friction, that is called major head loss, and head loss due to the pipe fittings, that is called minor head loss. How will figure out? This is the equation to figure out the major head loss. This is the equation to figure out the minor head loss. And in minor head loss, you see this value is constant. So you just need to figure out the value of KL. You might get KL1 plus number 2 fitting KL2, then value of KL3, then you add all them together and you multiply by B square by 2G. How will you get the V? Q by A, right? So let's go through the next slide. Now, how we'll figure out the all the KL factor? So if you are, say, designing a pipeline, your company, or there is a lot of handbook, and also you will see company website, especially SME website, you will see a lot of data is given, like how much will be lost in a T joint, in a elbow, or in a valve. You see right over here, this is a tank. With the tank, there is a attached a pipe. And you see, this is a difference between this one and this one, because pipe enter a little bit inside. So in that case, what will be your value of KL? You see over here, KL equal to 0.8. But right over here, if you have sharp edge, KL equal to 0.5. And right over here, you see in the corner, they have a radius. Right over here, it's saying radius, this radius, okay? This is a corner, but no radius, sharp edge. Right over here, you see there is a radius kind of fillet, right? So in that case, is R by 2 greater than 0.2, then KL will be 0.03. It 0.1, then 0.12. Similarly, if you like over here, this one in opposite of this one, water is getting out from the tank and water is entering in that tap. So in that case, it's just opposite of this figure, flow in opposite direction. It's a K equal to alpha, right? Let's see what is value of alpha. It's saying if alpha for alpha equal to 2, if flow is laminar, that means KL will be 2. And if it's turbulent, then KL will be 1. Then if we look right over here, sudden expansion, that means you have a smaller pipe, attach suddenly a bigger pipe. This is diameter small d, this is bigger d. In that case, what will be your certain expansion, right? Right over here. So in that case, you need to use this equation. That means small d square divided by big D square 1 minus then whole square. This is the value of KL. But if you have certain contraction, that means flow same configuration, but flow is coming from this side. You see, from the expansion tank, this is bigger diameter, this is smaller diameter. Then certain expansion contraction is happening. In that case, how will figure out the losses? So in that case, you need to use this chart. So in the chart, you see value of D square, smaller diameter pipe divided by bigger diameter pipe, then you go upward. And if it's 0.4, from 0.4, you go to the left side, you'll get value of KL. Okay. Now, okay, we have 10 minutes. After 10-minute session will be end. Then I'll give you second link. Okay. Now, right over here, you see expansion and the contraction is happening at the surface. That angle is 90 degree. It produces little bit more head loss. So instead, you can use gradually increasing or gradually shrinking. Like over here, your fluid coming from left side, and gradually right over here, diameter is gradually increasing. So we put some angle. If this angle is theta, so how you figure out this angle? You extend this line and this line. Then if I say horizontal, the total inclination angle between the two inclined surface, that is theta. That means this one inclined surface, other on this one. This is total angle theta. Okay. And sometime in the problem, if this angle is given, then when you have to figure out theta, say this is given 15 degree, then actually theta will be 30 degree, and figure out the value from this formula. Now you see they are giving value theta equal to 20, 45, 60 KL value 102, 04, 07. If it's 30, how will figure out? Just you need to extrapolate, because for 20 degree 0.02 and 45 degree 0.04, then you figure out the intermediate data for theta equal to 30 or theta equal to 25, what will be the value. Okay. And this one is same, this one is certain expansion, but in that case sudden contraction. That means dimension or diameter of the pipe gradually decreasing. In that case, this will be your friction factor for different angle. Okay. But this one is given this angle equal to theta, and this value, instead this one given directly instead of angle. By over here, instead of angle, they are giving value by ratio of small d by bigger D. So you need to be a little bit careful. And this data they are giving for theta equal to 20 degree. There may be another data theta equal to 30, 40. If you look in the handbook during the design, then you can figure out that data. So if we summarize that what we have, this is the equation for measured head loss, frictional head loss. And if his flow is laminar, you can directly figure out F equal to 64 by RE. If flow is turbulent, then you need to use a diagram. We'll show you how it look like, or you need to figure out from this equation value of F. And E by D, epsilon, not E, sorry, is the epsilon is the surface roughness, and D is the diameter of the pipe. And you need to figure out the Reynolds number, and all the data, if you put in a scientific calculator, you can figure out the value. Then how will know flow is laminar or turbulent? By Reynolds number. We already show you, right? Now, how look like the Moody chart? We can look like over here. This is the Moody chart. So you see in a previous equation, right, how many variable we have? We have variable F, epsilon by D, roughness by pipe diameter. Then you have Reynolds number. These three variable, he put in three axes to make a graph. Along vertical axis, in the right side, we have surface roughness, relative roughness. That means epsilon by D ratio. Along horizontal axis, Reynolds number, and increasing Reynolds number along this direction, right side, your surface roughness increasing along this direction, and your friction factor in the left side along vertical axis. Now, how will you use your equation? At first, you'll figure out epsilon by D, but you need to remember this epsilon, surface roughness, might be given in inch or millimeter or micrometer, but D and surface roughness, you have to be put in the same unit, because this is unitless, otherwise your result will be wrong. Say for a particular situation, you got E by D, you got 0.5. Say, so 0.5 mean your point over here. Then you figure out the Reynolds number, and you got Reynolds number. You see Miller's number, how it working. Right, this one, this logarithmic scale, this one 10 to the power 5, this one 10 to the 2 into 10 to the power 5, this one, okay. Then 3 into 10 to the power 5, 4 into 10 to the power 5. Then right over here, it become 10 to the power 6. Say a particular situation, you got 10 to the power 6. So you move from 10 to the power 6, or say you got 8 into 10 to the power 5. So you are moving upward, right? Make a line with the pencil. Now we look over here. So your surface friction right over here, you come to the left. So directly your friction factor, you are right over here, about 0.03. But for example, you are right over here, but your Reynolds number right over here. Now, how will figure out the value? So in that case, say over here, I need that one. Okay. Now from here, you need to come write this line. And how you can go there? You see this point between surface friction 0.6 and 0.4. So if there is a one more line, you draw a similar line, that line go in between this line, that means this line and this line, right? So if I took a blue line, that means you need to go make a similar line all the way between these two lines until it's hitting over here. So now it's coming right over here, right? Now you go to the left side, figure out your friction factor. But in first situation, right, 10 to the power 6, you are not worried that much because this portion you see almost straight line, like this portion from here to here, again from here to here. But if your Reynolds number is not in the flat portion, that means straight line portion, then you have to make a line between the point. For again, for example, particular situation, your Reynolds number you got right over here. Okay. Now your surface friction is right over here. Then how will go? Then you need to go through along the direction, through this line, between this line and this line. Then you have to make a turn a little bit, then right over here. Then you go straight left side. Okay. So if you use Moody diagram, you can figure out for both laminar and turbulent flow. It will be same. That means this region, left side region is the laminar flow, and right side region is turbulent flow. So by using Moody sum, you don't have to look.